In the spring of 1925, a letter arrived at Harvard College Observatory from Sweden. It was written by Gustav Mittag Leffler, one of the most respected mathematicians in the world, and it was addressed to a woman he had never met. He wanted to nominate her for the Nobel Prize in Physics. The letter was 4 years too late. The woman he was writing to had been dead since 1921, buried in a quiet cemetery in Cambridge, Massachusetts, her grave marked by a simple stone that gave no hint of what she had done. Her name was Henrietta Swan Leavitt, and without her, we would have no idea how big the universe is. This is the story of a woman who, working in near total obscurity, paid 30 cents an hour, never given a telescope of her own, never invited to the meetings where men discussed the cosmos, discovered the single most important measuring stick in modern astronomy. Her discovery is the reason we know there are other galaxies. It is the reason we know the universe is expanding. It is the reason we can talk about the Big Bang at all. And almost no one knows her name. To understand what Henrietta Leavitt accomplished, you have to understand the world she walked into. In the late 1800s, astronomy was undergoing a revolution. For thousands of years, astronomers had simply looked through telescopes and written down what they saw. But in the 1880s, photography changed everything. Suddenly, a single glass plate, exposed to the night sky for hours, could capture more stars than a human eye could ever count. The trouble was, somebody had to count them. Somebody had to measure them. Somebody had to compare them across hundreds of thousands of plates. And that work was tedious, repetitive, mathematical, and considered far too boring for any serious male scientist to bother with. Enter Edward Charles Pickering, the director of Harvard College Observatory. Pickering was a brilliant administrator and, by some accounts, a man growing increasingly frustrated with his male assistants. According to legend, he once declared that his Scottish housekeeper could do a better job than the men he was employing, so he hired her. Her name was Williamina Fleming, and she was a single mother who had been abandoned by her husband. Within a few years, she was running a small army of women who became known as the Harvard Computers. They were paid between 25 and 50 cents an hour, less than a typical secretary, less than a factory laborer. They worked 6 days a week, 7 hours a day, hunched over photographic plates with magnifying glasses and notebooks, doing the painstaking, exhausting work of cataloging the heavens. Henrietta Swan Leavitt joined this group in 1893. She was 25 years old, the daughter of a Congregationalist minister, a graduate of what would become Radcliffe College. She had studied astronomy in her senior year and fallen in love with it. But after college, something happened that would shape the rest of her life. She contracted a serious illness, possibly meningitis, that left her progressively, severely deaf. By the time she walked into Harvard Observatory, the world had already begun to fall silent around her. She started as a volunteer. She wasn't paid for the first several years. She simply showed up, sat at her desk, and did the work. Pickering eventually put her on the payroll at 30 cents an hour. He gave her what he considered a manageable task: find variable stars. A variable star is a star whose brightness changes over time, sometimes slowly, sometimes in a regular rhythm. They were considered scientifically interesting, but mostly as curiosities. Pickering wanted Leavitt to look through photographic plates of the Magellanic Clouds, two fuzzy patches of light visible in the southern sky, and pick out every variable star she could find. This was not a task anyone expected to produce a major scientific breakthrough. It was data entry. It was bookkeeping. The plates would arrive from a Harvard outpost in Peru, where they had been taken by male astronomers under the southern stars. They would be shipped back to Cambridge, and there, Leavitt would compare plates of the same patch of sky taken weeks or months apart, looking for tiny pinpricks of light that grew brighter and dimmer over time. She did this thousands of times, tens of thousands, hundreds of thousands. By 1908, she had identified 1,777 variable stars in the Magellanic Clouds. It was an astonishing number, more than anyone in the world had catalogued. But Leavitt didn't stop at counting. As she worked, she began to notice something that the men around her had missed. Among the variable stars she was finding, there was a particular type called Cepheid variables. These are massive, pulsing stars that swell and shrink in a regular rhythm, brightening and dimming on cycles ranging from a few days to a few months. And as Leavitt examined them, she noticed a pattern. The brighter the Cepheid, the longer its cycle. This sounds like a small thing. It is not. It is, in fact, one of the most consequential observations in the history of science. Here's why. Imagine you are looking at a row of street lamps stretching off into the distance. The lamps closest to you appear brighter. The lamps far away appear dimmer. But you cannot tell, just by looking, whether a particular dim lamp is dim because it is far away or because it is a low wattage bulb. Without knowing how powerful each lamp truly is, you cannot tell how distant it is. This had been the central problem of astronomy for centuries. When we look up at the night sky, we see stars at different brightnesses, but we have no way of knowing just from looking whether a bright star is genuinely bright or just nearby. The cosmos is a smear of light with no depth, no scale, no measurable distance. Leavitt's discovery was the answer. If you find a Cepheid variable and you measure how long its cycle is, you can calculate how bright it actually is, how powerful that light bulb really is. And once you know how bright a star truly is, you can compare that to how bright it appears, and from that, you can calculate exactly how far away it is. Cepheids became, in the language of astronomy, standard candles. They became cosmic measuring sticks. They became the rulers we use to measure the universe. Leavitt published her initial findings in 1908 in a paper that bore Pickering's name as the principal author, even though the discovery was entirely hers. The paper attracted only modest attention. She continued working, refining her observations, and in 1912, she published a more detailed analysis based on 25 Cepheids in the Small Magellanic Cloud. This time, the relationship was unmistakable. A precise, mathematical law connecting the period of a Cepheid's pulsation to its true brightness. Once again, the paper was published under Pickering's signature, with a single line near the beginning that read, "The following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt." That sentence is, perhaps, the quietest revolution in the history of science. Within a few years, astronomers across the world began using Leavitt's law. The Danish astronomer Einar Hertzsprung used it to measure the distance to several Cepheids in the Milky Way. The American Harlow Shapley used it to map the structure of our own galaxy, and figured out for the first time that our solar system was not at its center. We were on the outskirts, halfway out toward the edge, just one of 100 billion stars whirling around a distant galactic core. But the moment that everything changed, the moment when Henrietta Leavitt's quiet little observation cracked the universe wide open, came in 1923. That year, an astronomer named Edwin Hubble was using the brand new 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world. Hubble had been studying a fuzzy patch of light in the constellation Andromeda. For decades, astronomers had argued about what these fuzzy patches were. Were they clouds of gas inside our own galaxy? Or were they something else entirely? Other galaxies, separated from ours by unimaginable distances. Nobody could agree, because nobody had any way to measure how far away they were. And then, on the night of October 5th, 1923, Hubble found a Cepheid variable inside the Andromeda Nebula. He measured its period. He applied Leavitt's law, and he calculated that it was 900,000 light-years away. The number was almost too big to comprehend. It was 3 times farther than the largest estimate anyone had ever made for the size of the entire universe. And it meant, undeniably, that Andromeda was not inside our galaxy. Andromeda was its own galaxy. A separate island of hundreds of billions of stars, drifting through a darkness so vast that the light from its furthest reaches takes millions of years to reach us. Modern measurements, by the way, place Andromeda even further away, around 2.5 million light-years. In a single night, the universe had multiplied. There were not just stars out there were galaxies, maybe hundreds of them, maybe thousands, maybe, as we now know, 2 trillion. Hubble continued using Leavitt's law to measure distances to other galaxies. And he noticed something even more astounding. The galaxies were moving away from us. The further they were, the faster they were moving. The universe was expanding. From this single observation, scientists worked backwards, all the way to the beginning, to a moment when the entire cosmos was a single, hot, dense point, to the Big Bang. Every step of that revolution, every measurement, every distance, every estimate of how big and how old the universe is, rests on the work that Henrietta Leavitt did, hunched over a photographic plate, paid 30 cents an hour, in a room she shared with other women who were not allowed to operate the telescopes, whose images they spent their lives analyzing. She never knew. She never lived to see what her discovery had unleashed. By the time Hubble made his measurement in 1923, Henrietta Leavitt had been dead for 2 years. She had been diagnosed with stomach cancer in 1921. She was 53 years old. She had spent the last several years of her life suffering, frequently sick, frequently at home, but always returning to her plates. Even on her deathbed, she was reportedly still concerned about completing her measurements. When she died, her family found that she had left almost nothing behind in worldly possessions. A small library of books, a modest bank account, some notes, a telescope, which she had been unable to use in any meaningful scientific way during her lifetime. 4 years later came the letter from Mittag Leffler. He had read her papers. He had seen what she had done. He wanted to nominate her for the Nobel Prize. He wrote to Harlow Shapley, by then the new director of Harvard Observatory, asking for more details about Leavitt's life and work so he could prepare the nomination. Shapley's reply was, depending on how charitably you read it, either pragmatic or appalling. He explained that Miss Leavitt was deceased, that she could not receive the prize. And then, in a move that historians have raised eyebrows at ever since, he subtly redirected attention toward his own work using her discoveries, suggesting that any prize for the period-luminosity relationship should perhaps go to him. The Nobel Committee does not award prizes posthumously. The matter ended there. Henrietta Leavitt was, in fact, never officially recognized in her lifetime as the discoverer of the law that bears her name. Pickering was the listed author on her major papers. When other men used her work to make their own famous discoveries, they often cited it briefly and moved on. She was, in the standard manner of the era, treated as a kind of human instrument, a tool that produced data. The fact that she had also produced a theoretical insight, a mathematical law, a key that would unlock the size of the cosmos, was simply, in many circles, ignored. In recent decades, this has begun to change. Astronomers today refer to the period-luminosity relationship as Leavitt's law. There is an asteroid named after her. There is a crater on the moon named after her. Her papers have been reread, her contribution re-examined, her place in history slowly, belatedly restored. But it is still the case that the average person on the street has never heard her name. We know Newton. We know Einstein. We know Hubble, who used her ladder to climb into the cosmos. We do not, mostly, know the woman who built the ladder. There is something almost unbearable about her story when you really sit with it. A deaf woman, working in a room full of other women, all of them paid less than the men who cleaned the building. None of them allowed to use the telescope. She makes a discovery so profound that it redefines the size and age of everything that exists. She publishes it under another man's name. She dies in pain, in obscurity, before anyone fully understands what she has done. And then, decades later, when the full weight of her contribution finally becomes clear, the man who could have championed her legacy quietly tries to take credit for it. And yet, when you look up at the night sky tonight, when you see Andromeda, that little smudge of light in the autumn sky, and you remember that it is 2.5 million light years away, that the photons hitting your eyeballs left that galaxy when our ancestors had not yet learned to make stone tools, you are seeing the universe through Henrietta Leavitt's eyes. Every galaxy ever measured, every estimate of the age of the cosmos, every diagram of the expanding universe in every textbook in every classroom in the world, all of it, every single number, is built on the foundation she laid down with a magnifying glass and a notebook in a room in Cambridge, Massachusetts, more than a century ago. She did not calculate part of the universe. She gave us the means to calculate all of it. And she did it for 30 cents an hour, while she was going deaf, while she was dying, while the men around her published her findings under their own names. Her gravestone is still there, in Cambridge Cemetery. It is plain. It bears her name and the dates of her life. It does not mention what she did. But somewhere above it, every clear night, the stars she counted are still pulsing in the rhythm she discovered, marking distances she was the first human being to ever truly understand. Henrietta Swan Leavitt, born July 4, 1868, died December 12, 1921. The forgotten woman who measured the universe.